All right, so this video is going to be a special case of constant acceleration called free fall. Free fall occurs only when an object is only acted upon by gravity. So if you throw something straight up in the air, from the moment you let it go, the only thing slowing it down as it goes up is gravity. Then it goes to the top and comes back down. And as it's coming back down, before it hits the ground again, the only force acting on it is gravity. Okay, and if you take two objects, okay, regardless of their mass, they are going to accelerate at the same rate. On Earth, there is a little bit of an air resistance factor that slows things down more than you can take a textbook and a piece of paper, and if the piece of paper is flat, the book's going to win because of air resistance. But on the moon, where there's no air resistance, they fall at the same rate, as you're going to see with this video.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So as you saw, those two objects fell at the same rate on the surface of the moon. Okay, they were in a state of free fall. They were falling only due to the force of gravity pulling on them. Now, if we look at our motion maps, motion graphs versus velocity versus acceleration graphs, or velocity versus time graphs, here's what we get. Okay, so an object dropped from rest is going to speed up as it goes down. Its acceleration is downward. Okay, and that velocity then, because the acceleration is downward, our velocity is going to get more negative as it falls away from the origin. Okay, so the velocity versus time graph looks like this. It actually speeds up as it goes away. Now see, the object is initially moving upward, so we throw it upward, but in this case it's slowing down. Our acceleration is still downward because our object is slowing down as it goes up. So we still get a negative slope as we go up, as you throw something up. Okay. So again, the graph shows, okay, for all falling objects. Okay, free fall, okay, always goes downward. It's always negative, no matter what direction the object is moving, because as you go up, the object is slowing down upward, which is really going negative acceleration. Okay, as it comes back down, it's speeding up, going towards the ground. Again, a negative downward acceleration of 9.8 meters per second squared, vertically downward. A lot of times you just be able to use 10, but it is 9.8. Okay, so G is by definition positive. There'll never be a problem that uses a negative G. So even though an object is falling up, it has a negative acceleration. Okay, but because free fall is motion with constant acceleration, we can use kinematics equations for constant acceleration with AY is equal to G. So if you're dealing with free fall, your AY is G. Okay. Again, the third bullet from the bottom is big. G is not called gravity. It's the free fall acceleration, really the acceleration due to gravity. And again, G is only 9.8 on Earth. Other planets have different values of acceleration due to gravity, free fall acceleration. Okay. Sometimes in certain problems you will use it in terms of G, 1G, 2Gs, 3Gs. Okay. So if we look at this, we have this, you launch a rocket straight up, you throw a ball straight up in the air. Okay. So it goes up, stops here, turns around, and comes back down. Okay, it says at which point in the trajectory is the arrow's acceleration the greatest? So here's the thing, that the acceleration is consistent all the way up. All the way up, its acceleration is 9.81 in the negative direction. As it comes back down, 9.81 in the negative direction and downward direction as well. So the accelerations are constant. Okay, now if you look at the velocities here, as the object goes up, 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 the velocity decreases. Up here, its velocity here is 0, but it only happens there for a moment. Okay, then as it comes back down, it speeds up, 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 up. Okay, but if at B and D and A and D, A and E, they have the same velocities or the same speeds. They're just going in different directions. Here's why. And B and D have the same thing as well. From A accelerates up. A is going to negative accelerate, slow down to B. Okay, and it's going to slow down to C. Acceleration is the same rate. Now, from B to C is the same time interval as from C to D. So because their acceleration is changing at the same rate, or their acceleration is constant, the time intervals are the same. So we're going to get an equal change in speed. So B's speed is equal to D's speed, A's speed is equal to E's speed. Okay, and acceleration is the same at all points. Okay, so we drop something. So we drop a rock, falls 100 meters before hitting the ground. Okay, we're going to look at how long does the rock take to fall to the ground and what's its velocity when it hits. Okay, so we know that it's accelerating. We know its initial height. We know its final height is 0. We know its initial speed is 0. Okay, because we're just going to let it go. We're not going to throw it down. It just says dropped. Okay, and y is equal to negative 9.81. We're going to figure out how long it was in the air and its speed when it hits the ground. All right, so now we're going to use the kinematics equations again. Okay, we know y final. We know y initial. Okay, we don't know t, but we know a. Okay, we know our initial velocity is 0 and our y initial is 0. Okay, ay is g. Okay, so we can rearrange the equation to solve for t, which is really 2 times our distance divided by gravity and the square root of that. So it falls 4.5 seconds. Okay. Rearrange this equation to solve for TF. And now because we know the time, and we know acceleration due to gravity, and we have no initial velocity, we can use this equation, this kinematic, to solve for our final speed of negative 44.3 meters per second. And it's negative because it's going down. Okay. Again, you might want to look over that again, make sure you understand how to do it. Okay. And there's your rationale that it is about right. Okay. Now, we have this object, this leaping antelope. Okay. Springbrook goes into a crouch and to perform a jump, a pronk. Okay, it then extends its legs forcefully, accelerating at 35 meters per second for 0.7 meters as its legs straighten. Okay, it leaves the ground and rises into the air. Okay, so if we look at this, we know that we want to figure out, as it pushes off the ground, how high it goes, or what's its speed when it goes off, because we know that its initial velocity is 0. We know that its acceleration is 35 meters per second, and we know that it goes up to a y final height of 0.7 meters. Then we want to figure out how high does it get up in the air. Okay, we need to figure out the initial launch speed, which is actually equal to the final speed over here. So it's a multi-step, multi-part problem. Okay, so let's look at this one. So the first problem, we know its initial position is 0. We know its initial speed is 0. We know its acceleration is 35 meters per second. And we know that because the legs get fully extended of 0.7 meters off the ground, we need to solve for VF. So with that, we're going to use this equation right here. Why? Because we know VI is 0, we know A, and we know delta Y. So we can use this equation to solve for Vy final, which is 7 meters per second. So that means that when this thing leaves the ground, its speed that as it leaves the ground is 7 meters per second. Okay, so at an acceleration of 35 meters per second over a distance of 0.7 meters, its final speed right before it leaves the ground is 7 meters per second. Now we want to figure out with that 7 meters per second launch speed, how high does it get off the ground? Okay, so we know that its Vy initial is going to be 7. Vy final at the very top of its launch is going to be 0 because it stops moving at that point. And we know the acceleration due to gravity is negative 9.8 meters per second squared. So now we're going to figure out how high does it go. Okay, motion map here. Slowing down as it goes up, so its acceleration is down, it's a negative acceleration. Okay, so because we know Vy final is 0, Vy final is 0, Vy initial we know G, we know delta Y. Okay, so we can use this equation here. Vy final is equal to Vy final squared is equal to Vi initial squared minus 2G delta Y. Okay, but because our final velocity is 0, then it says 0 is equal to this. Okay, which if you rearrange it, because the final is 0, we get this. So our final speed then is going to, or excuse me, our final distance or displacement is going to be Vy initial squared divided by 2G. Okay, so our Vy initial that we got in the previous problem is 7 meters per second, divided by 2 times 9.81 meters per second squared. 7 divided by about 20 is 2.5. So he jumps 2.5 meters up into the air. Okay. All right. So we have a free fall. Okay, on something called Great Drop. There's one like it's the Extreme Scream at Knott's Berry Farm. Okay. The cars are then released for 2.6 seconds of free fall. How fast are the passengers moving at the end of this speeding up phase of the ride? And if the cars in which they ride come to a rest in a time of 1 second, what is the acceleration of the slowing down phase of the ride? Given these numbers, what's the minimum possible height of the tower? Okay, so a lot of stuff to do on this one. So we're looking for how fast are the passengers moving at the end of this 2.6 second free fall. And after that 2.6 second free fall, if the cars in which they ride come to a rest in time of 1 second, what's that acceleration of the slowing phase? So from whatever speed this is to a stop in 1.0 seconds, what's the acceleration? And then we got to figure out if all this happens, what's the minimum height possible for the tower? So let's take a look at what we know. Okay. We know the drop height, or excuse me, we know the drop time. So here are your answers to that problem. Okay. So we know that the object is accelerating at a rate of 9.8 meters per second squared. And we know that it falls for 2.6 seconds. So 2.6 times 9.81 meters per second squared gets us a final velocity of 25 meters per second. Okay, so to decelerate or to slow down from 25 meters per second to 0 in 1 second means that we have to go 25 meters per second squared is the acceleration upward. Okay, so the brakes have to apply at 25 meters per second to stop it. Okay, now to find the height, okay, we break the motion into two different parts. The first phase is just the drop. Okay, 1/2 because we're looking for our final distance. Our initial distance is 0, so final distance is 1/2 acceleration due to gravity times time squared. Okay, we know our time is 2.6 seconds, so 1/2 times acceleration due to gravity times our time squared is 33 meters. So it free falls for 33 meters. The second phase, we know the acceleration is 25 meters per second squared. We know our time interval is a second, so 1/2 25 times 1 second squared is 12.5 meters. So we have 33 meters for the drop, 12.5 meters for the brakes, so the total distance that it falls is 46 meters. Okay. Now, again, with that, you're just going to have to go back and review, and we'll go through some more problems in class. All right, so again, look at this graph here. Okay, when an object is in free fall, the velocity becomes more negative when it's coming back down. This part right here, the Vy from that where the y-axis to the 0 on the time, this is when it's slowing down going up. This part down here is when it's coming back down to Earth because it's speeding up, but it's speeding up in a more negative direction. It's becoming more negative. Okay, and that's the end of the free fall video. Answer the questions on your formative assessment, and we'll talk more about this in class. Have a good day.